Hey everyone, and welcome. Today, we are diving deep into one of the most fundamental and coolest ideas in all of computer science, algorithm complexity. We're going to figure out how we measure code, not just in seconds or minutes, but in a way that truly lasts. So let's start with a basic question. If you and I both write a program to do the exact same thing, how do we know which one is actually faster? Now, the obvious answer is, well, just time them. But think about it. What if you're running it on a brand new gaming rig and I'm using a laptop from 10 years ago? Your code would seem faster even if it's not. See, time alone is a really bad metric. It's always changing. We need something better, something universal.
And that universal ruler is what we call input size. We just use the letter n to represent it. So instead of counting seconds, we count how many steps an algorithm has to take as n, the size of our problem, gets bigger and bigger. Are we sorting a list of 10 numbers or are we sorting 10 million? That n is the key to understanding how an algorithm is going to behave in the real world.
But there's another wrinkle. Even for the same n, an algorithm doesn't always do the same amount of work. Think about looking for a word in a dictionary. The best case, you're looking for apple, and bam, it's right there at the beginning. The worst case, you're looking for zebra, and you have to flip through every single page. And the average case is, well, somewhere in the middle. Now, in computer science, we're usually pessimists. We plan for the worst-case scenario because that gives us a guarantee. We know it will never be worse than that.
Okay, so we're measuring work based on the input size n, and we're usually focused on that worst-case scenario. But how do we actually describe that relationship? How do we say this algorithm's work grows slowly versus this one's work just explodes when n gets big? For that, we need a special kind of language.
And the most famous part of that language is big O notation. Just think of big O as the ceiling. It sets an upper bound. It's that pessimist's view we were talking about. It tells us that an algorithm's performance will be no worse than this particular growth rate. It's the most common way we talk about this stuff because it pins down that worst-case performance we care so much about.
On the other hand, if you have a ceiling, you've got to have a floor, right? That's big omega. This is the optimist's view. It gives us a lower bound, guaranteeing that an algorithm will take at least this much effort to finish, even on its best day.
And finally, you get the realist's view, big theta. This is what we use when the ceiling and the floor are basically the same. It gives us a really tight, precise bound on performance. It's like saying the algorithm's growth is perfectly sandwiched between these two lines.
All right, let's make this real. Imagine we analyze some code, and its workload looks like this function: 3n squared plus 5n plus 10. Now, when n gets massive, like a million or a billion, that n squared term becomes so unbelievably huge that the other parts, the 5n and the 10, they're like dust. They don't even matter. Even the 3 out front doesn't really change the shape of the growth. What really drives everything, the dominant term, is n squared. So we just drop all the fluff and say the complexity is big O of n squared.
Now that we have this language, we can start to see this huge divide in the world of problems. On one side, you have polynomial time problems. We call this class P. These are the tractable ones, the ones we consider fast. Their complexity is something like n squared or n cubed. But on the other side, you have the monsters, non-polynomial problems. Here, the complexity grows exponentially, like 2 to the power of n. These things become so slow, so fast, that they're basically impossible to solve for even a medium-sized n.
This brings up a really interesting type of problem. You know the kind I'm talking about. The ones that are an absolute nightmare to solve from scratch. But if somebody just walks up and hands you a possible solution, you can tell if it's right or wrong in a snap. Where do those problems fit in?
Well, they fit into a class called NP. And this is so important. NP does not stand for non-polynomial. It actually stands for non-deterministic polynomial time. The key idea here is all about verification. A problem is an NP if, when I give you a yes answer, you can check if I'm telling the truth efficiently in polynomial time.
Let's just pause on that for a second. Class P has the problems we can solve fast. Class NP has the problems where we can check an answer fast. That's a huge difference. And if you think about it, if you can solve a problem fast, you can definitely check a solution fast. So every single problem in Class P is also in Class NP.
Okay, but here's where it gets crazy. Inside this massive universe of NP problems, there's this very special, very exclusive club. These are the certified heavyweights, the absolute hardest problems in all of NP.
And these are called the NP-complete problems. To get this title, a problem has to pass two tests. First, it has to be in NP itself. Easy enough. But second, and this is the mind-bending part, it has to be so fundamental that every other problem in NP can be cleverly disguised or reduced to look like an instance of this one problem. It's like a master key for the entire class.
And that reduction leads to this absolutely profound idea. Because any problem in NP can be transformed into any NP-complete problem, if you could somehow find a fast, polynomial-time solution for just one of them, you'd break everything. You would have a fast solution for all of them overnight.
So let's meet a few of these legends. First up is 3SAT. This is the original NP-complete problem. It sounds simple. I give you a really long, complex, logical formula, and you have to tell me, is there any combination of true and false values that makes the whole thing come out true?
Then you've got vertex cover. Imagine a map of cities and roads. The question is, can you put guards in, say, K or fewer cities so that every single road on the map is being watched by at least one of those guards? Simple to describe, brutally hard to solve.
And then you have a related group, NP-hard. These problems are at least as hard as the NP-complete ones. The big difference is they don't even have to be in NP, which means checking a solution might also be incredibly difficult. The most famous example is the traveling salesman problem, trying to find the absolute shortest route that visits every city on a map just one time. It's a legendary challenge.
So why does any of this matter? This isn't just abstract theory. The very hardness of these problems is what modern cryptography is built on. It's what keeps your data safe. It defines the practical limits of what our computers can and can't do, and for programmers, it's a huge signpost that says, hey, don't waste years trying to find a perfect, fast solution here, because one probably doesn't exist. It tells us when to look for good enough answers instead.
And this all leads us to the single biggest unsolved mystery in computer science, a problem with $1 million prize. Does P equal NP? If the answer is yes, if it turns out that every problem that's easy to check is also easy to solve, our world would transform in an instant. We could crack complex problems in medicine, logistics, and material science. Online security as we know it would shatter. It's a question about the fundamental nature of problem solving itself, and for now, nobody on Earth knows the answer.